power estimation, we are going to discuss about how to estimate average power in combination circuit. Average power can be estimated by simulating the circuit with a large number of n of inputs. If the successive input patterns are independent, then the average power can be estimated from load, switching activity or large Q. However, in order to determine the value of capital N, statistical mean estimation techniques can be used to determine the stopping criteria. It's like a T distribution. The power consumed by a circuit over a period T has a normal distribution. Let P dash and S be the average measured and the standard deviation of the random sample of the power measured over time capital T respectively. Then 1 minus alpha into 100% confidence, we can write the following inequality. This is mean value P bar minus P average, it's a modulus, is less than T alpha by 2 S divided by square root of capital N. So this is the inequality. The switching activity can be estimated by using the T distribution. So S is the mean value, square root of N is the sample. The quantity Tn minus 1 alpha by 2 is obtained from the T distribution function with the n minus 1 degrees of freedom, and P average is the true average power. So mean minus average divided by mean value, P bar is the mean value, is less than T alpha by 2 S divided by this P bar square root N. From the above inequality, one can notice that the right hand side of the inequality should be less than epsilon, the desired percentage error for the given confidence level 1 minus alpha into 100%. Hence, the following condition should be satisfied. T alpha, this is equal to less than the error, percentage error. So, therefore, the above equation can determine the required number of simulations capital N for obtaining a given confidence level and desired percentage error. So, the capital N is greater than or equal to T alpha by 2 S divided by P bar epsilon the whole squared. A simple modification to the above Monte Carlo technique can be used to accurately estimate the internal load power dissipation by considering the absolute error bound for low activity nodes rather than the percentage error bound. Let us consider a circuit that is simulated capital N times for a time interval capital T. Let the number of transitions measured at a node every time be n small I. Small I is 1 to capital N. Hence, the average number of transitions at the node is given by n bar is equal to ni slash capital N. Then, according to the central limit theorem, n bar has the distribution that is close to normal for large values of capital N. If beta is the true expected value of the average number of transitions at the node under consideration and S is the measured standard deviation of capital N values of Ni. So then the following inequality holds 1 minus alpha into 100% confidence, beta minus n bar divided by n bar is less than or equal Z alpha by 2, that is suffix S divided by n bar into square root. So Z alpha by 2 is obtained from the normal distribution. For the above inequality to be valid, n should be larger than 30. As before, if the percentage error can be calculated, tolerated is epsilon, then the number of required simulation is this one. N is greater than or equal to Z alpha by 2 S divided by epsilon n bar the whole squared. It is clear from the above inequality that is n bar is very small, then the number of simulation runs n will be very large. Hence, for the low active nodes for which n bar is less than beta minimum, the following modified stopping criteria. So you use this is for beta minimum. Hence, from inequality, the above equation can be written as beta minus n bar is less than or equal to z alpha by 2 s divided by square root is less than or equal to beta minimum epsilon. So this is an absolute error bound for low activity nodes. The next one, we have to estimate the switching activity of power in sequential circuits. You consider the sequential circuit. This is combinational. It has a present input, present output, that is primary output. It goes to the next state input. This is present state input through the registers, latches. Okay. Now here one state diagram is given. It has 4 states. State 1, 2, 3, 4. Okay. Then the input is also specified. So this input defined where it goes from which state to the another state. So from this state diagram, this logic diagram can be done. It has an input state 1, state 2, that is states. This is n, next state 1, next state 2. Okay, so from the state diagram, draw the state table. From the state table, we draw the logic diagram. So actually, the switching activity in the sequential circuit, the next output depending upon the present input and the present state inputs. Okay, so this is purely depending upon the state diagram. If the state diagram done properly, this glitches can be avoided. So what it does means, at a time 2-bit change will not be accepted. Only single bit change will be accepted. That you have seen in the next slide. Let us assume that the input signal distributions are represented by probabilities and activities of the input. Therefore, given an STG, state transition graph of one finite state machine, we can create an extended state transition graph. Each state in ESTG is represented by the present state ESTG, and the next primary input vector. The temporal correlation of the input signals are explicitly represented by an ESTG. So this is extended state transition graph. It states that there is a state 1 and state 2, at least only one bit change is accepted. So the previous state diagram can be redrawn is like this. So S1, you add 1 bit. The changes in the least significant bit. This is for 0. That is 1 transition. S2 for 0 transition, 1 transition. S3 0 1. S4 0 1. Okay. Now the input is drawn based on the previous thing. Method 1, to estimate the signal probability at the present state input, which takes spatial correlation. Spatial correlation is nothing but with respect to space and time of signals into consideration, but ignore any temporal correlations. Method 2, to accurately estimating switching activity in sequential circuits, use spatio-temporal correlation among signals. So based on this, signal probability is uptime, signal activity, state transition probability, transition state probability, and transition switching density, transition density, everything to be calculated. If the input changes from 0 to 1, the transition dynamic input. At the same time, depending upon the input slope, if the input slope is changing from 0 to 1 at a different nanoseconds. 1, 2, 3, that is the rise time. Okay, depending upon that, the power can be estimated.